I'm so pleased to be here today with you. And as I said, we are all the same. There is no small and big, and up or down. We are all the same. We all come from somewhere, and we all have a story that in a way it leads us to where we go and what we do. But at the end of the day, we as long as somebody believes in their abilities and believes in what they can achieve and work for to realize their dreams, they can do whatever they want. That's I believe in it. I believed in it when I was small, and I even believe it in more now. So and I always say that I was so lucky to be born not in a very privileged family or something like that. And the reason for that is I always think that if Van Gogh, who is one of the best artists in the world, I think if he was a millionaire or something like that, I believe he would not have done what he has done with his paintings and all that. So excellence always comes from a need. That's how I see it. So today, as I said, I'm so pleased to be talking to you. In particular, for me, Hawaii is very special. Every time I go there, to me, it's probably the best time I spent in the year. And I cannot forget the first time I was swimming and I saw a sea turtle for the first time. I've seen sea turtles before, but the ones I've seen in Hawaii they were very, very special to me. So this type of memories are always in my head. So, okay, I'm Nour Rawafi from the Johns Hopkins Applied Physics Lab. I am the project scientist for the Parker Solar Probe mission, which is one of the probably most outstanding missions that NASA has ever built. It's what we are learning from this mission is really well beyond what we ever thought. But before going into that, let me tell you a little bit about myself, and I'm going to say just a little bit because usually I don't really like to talk about myself. So I was born in Tunisia, which is a small country in North Africa, which is right here. That's Tunisia. And I grew up there until the age of 24. So I did all my undergrad studies in Tunisia, and after that I went abroad. I'll tell you a little bit the journey I did to get here to where I am now. But for you, if maybe you don't know that the name Africa is actually the old name of Tunisia. But after that, it was adopted for the whole country, for the whole continent. So Tunisia is, as I said, it's not a big country, but it's really a very nice one. So you have one of the best beaches in the world. We have mountains that are so beautiful as well, but we also have the desert down there, and which is really nice. And I'm gonna show you something now. If you can tell me, can any of you tell me what is this picture about? Any guess?
Go ahead.
So, okay, this is actually one of the sites where Star Wars was filmed, and it was in the south of Tunisia. So that's what it is. So if you are visiting Tunisia and you happen to be in the south, you can actually visit all this. It's like a small city where the whole that shooting was done, and it's still there. It's a huge touristic attraction, and by the way, in 2027 we will have a total solar eclipse that will go just across this region here, and I'm planning to organize a meeting there. So if I want to welcome all you to participate on that meeting, and you will be able to visit this site. So, okay, about a little bit more about myself. As I said, I grew up in Tunisia, and I did all my study until the undergrad in Tunisia. But as the top in physics over the whole country, there used to be a program there. If you are at the top, you get a fellowship to do whatever you want, wherever you want. So I got a fellowship. I went initially to Toulouse, which is in the southwest of France. I spent a year there, but after that, I moved to Paris to do my PhD. And from Paris, I spent, I think, something like 5 or 6 months afterwards in Italy. And then I went to Max Planck to spend 3 years there. And from Max Planck, I flew all the way to Tucson, Arizona, where I worked for the National Solar Observatory. The National Solar Observatory now moved to Boulder in Colorado. And after 4 years at NSO, I got an opportunity to move to APL. And one of the main reasons that led me to move to APL is that from the get-go, I knew that I'm going to work on Parker Solar Probe. So that one for me was the biggest incentive to make that big change. I was all settled down at NSO, but when this opportunity at APL came up, I couldn't let it go. So I jumped on it, and I got involved in Parker Solar Probe from the get-go. I've been on the mission now for 15 years. And just to let you know, as I was growing up, I never ever dreamed to have this journey. All I had in mind is really to work hard for whatever I wanted to do. And the other thing also that I keep it's in me, and I keep it always in me. My horizons is always moving, is always ahead of me, and also my target goals are always a moving target. I never say, okay, if I reach that point, I'm done, I'm going to stay there. It's always a moving target for me, which keeps me always like a driven person. That's how I like it to be. So okay, let me move a little bit to the sun. And since a very young age, I was extremely curious about the sun and also about stars in general. So I was born in the countryside, and during the night there, without light pollution, without anything, one of the most beautiful views you can ever have is the night sky, where you have the sky peppered with stars all over the place. Wherever you look, there is a star. And it's like that star is really shining at you. It's basically speaking at you. And obviously, when you think of it, the closest star to us is our sun. And if we are here on Earth now, it's in the most part of it is thanks to the sun, because the sun is what sustains life on Earth, and in a way it's responsible for our lives. But this is the sun as we see it with the naked eye. Obviously, this is a telescope image. That's why we see the sunspots. But with the naked eye, but we have to use filters, by the way. We cannot look at the sun directly. If there is a big sunspot with the right filters, you can actually see it with the naked eye. But that's basically what we see from the sun. But the sun is way more than this. When you look at it through instruments, and you discover the sun is way more complex than just a ball that is peppered with dark spots every now and then. So okay, let me talk about the event that we are all going to witness next week, which is the total solar eclipse. And this is an animation for the 2017 solar eclipse. So okay, what is a total solar eclipse? A solar eclipse, in a way, is a brief moment in the shadow of the moon. That's what it is. And when the moon positions itself between us and the sun, we get this really mesmerizing view of the outermost layer of the sun, that is the corona, that we cannot see with the naked eye, because it's very tenuous. And the emission from the solar disk itself is so overwhelming, so we cannot see the solar corona. But why it happens that we see that we have total solar eclipses? Because we are the luckiest people in the whole universe, that we have a special arrangement of the sun, moon, and earth, that the moon is 400 times smaller than the sun. But it's also the Earth-Moon distance is 1/400 times the Earth-Sun distance. So in a way, the angular size of the moon, as seen from Earth, is exactly the same as the angular size of the sun. But when the moon gets exactly between us and the sun, it's then when we get an eclipse. And it's not always a total solar eclipse. To get a total solar eclipse, the moon has to be in perfect positioning that it covers the whole solar disk. But sometimes when it is a little bit further out, we get what we call an annular eclipse. Basically, we have the whole disk is covered, but there is also a sliver on the edge that is not covered. That's why we call it annular eclipse. Anyway, when we have these total solar eclipses, we discover something that is so beautiful and so enigmatic. That is the solar corona. And this is an image of the corona from the eclipse of last year in Australia. And by the way, the colors you see here are true colors. They are two different lines. And when you superpose the emission from these two different lines, you get these beautiful structures in the corona. And by the way, the corona now is very complex because the sun is at almost a solar maximum. If you compare an image like this one with the eclipse in 2017, in 2017, it was simpler because we were at solar minimum back then. So in a way, the solar corona is always changing, and it's always complex as well. So what this tells us that the atmosphere of the sun is extremely complex, but we get an appreciation of it when you look at it through instruments that, in particular, in the ultraviolet, extreme ultraviolet, and also X-rays. You see that the sun is extremely dynamic. If you compare this movie that I'm showing here to the movie I showed earlier, that the image of the sun with the naked eye, it's like day and night. Here, the sun is changing all the time. There are plenty of structures, plenty of explosions on the surface of the sun, and it's all of that is done because the sun is a magnetized ball of plasma. That's what does all this. So if you go even a little bit further, you start seeing dynamics. It's not only that you see this small explosion very low down and all that. It's actually that the dynamics there will create this flow that we call the solar wind. And the solar wind is a torrent flow where you have material flowing at up to 800 kilometers per second. At that speed, you can get from the Earth to the moon in under 20 minutes. It's really, really high speeds. If you add to it images like these ones, and I'll wait for it to play a little bit, sometimes the sun will give you one of the best shows you can ever dream of. And this is one of them. Look at it. It's just amazing. When you look at an explosion like this one, which is a flare together with a coronal mass ejection, it is just fascinating, and it's we don't see this type of phenomena elsewhere. And by the way, when you take one of these events, the amount of energy in these events could fulfill our current power needs for 40,000 years. So these events, they carry amounts of energy that we cannot even imagine them. They are so energetic. As I said, one event is enough to power us for 40,000 years. Go a little bit further, and the show is even more enigmatic, more spectacular, these exposures we saw on the sun, and they are limited in space. They expand so much, and they engulf almost the entire space around the sun. And you see them going almost in all directions. Some of them go on this direction, some of them go in the other one. And by the way, it's not in this movie here, but Earth is somewhere here. These events actually reaches us, and they affect us in many ways. And one of the prime examples, I can show you later the movie. I'm pretty sure you are all familiar of the event when SpaceX lost 40 spacecrafts. It was actually due to one of these events that hit the Earth atmosphere, made disturbance there, and all those satellites has to decay down into the Earth atmosphere and burn. So these events are the driver of what we call space weather up there in space. And sometimes also their effect can even reach us here on the ground. I'm not sure if you are familiar with the power outage in the northeast of the US and Canada in March 1989. A huge swath of land in the east of the US and Canada all of a sudden went totally dark because one of these big events caused what we call a geomagnetic storm. It creates a lot of currents in the atmosphere of the Earth, and that their effect will get us to get to the power grid, and it shuts down the power grid completely. And if you think of it, these days we cannot live without electricity. We cannot live without our cell phones, without internet, without all this luxury around it. Actually, we can live, but I'm not sure we will enjoy it. That's the thing. So in a way, what I want to tell you about this, the sun is a magnetized dynamic star, and we need it to live. But on the other hand as well, we have to be really watchful for it, what it does, what it can do to us, because it can affect our atmosphere, it can affect our lives here on the ground in many different ways. So understanding the sun and how it works and all that is something that we need to always to keep in mind, and we need always to have it at the forefront of our interests. And Hawaii is not really strange at all. Some of the best solar telescopes are in Hawaii. In Maui, we have the largest solar telescope ever built. The Daniel Inouye solar telescope, DKIST. It's one of the best things we invented to study the sun. So, okay, to understand all this phenomena, the dynamics of the sun, the solar wind, all this explosive activity, we needed the spacecraft to get as close as possible to the sun. And the reason for that, we want really to get into that medium to get the action as it is happening, because when you are observing the sun from far away, you don't really get the fingerprints of the physics that cause this phenomena to happen. And there is no other way to do that unless you go really so close and personal with the sun. And that's what we did with Parker Solar Probe. But getting a spacecraft very close to a star is not an easy thing. It's not something we can do every day. We have been thinking about this mission for 60 years now. People start thinking about this in 1958. I believe most of us on this meeting here, we were not even born then. It took us 6 decades to come to this point, simply because we did not have the technology. If you don't protect your spacecraft when it is flying close to the sun, you can lose it in no time at all. It will just melt. And you have to be really watchful. The other thing also that we have to keep in mind, that when the probe is close to the sun, we cannot talk to it. So in a way, it has to deal with any potential problem on its own, because there is nothing we can do for it. So it has to be 100% autonomous. And that's what Parker Solar Probe is. Parker Solar Probe can function on its own without any human intervention for up to two months. And actually, we just came out of blackout period. We call these periods blackout periods. We came out of one of them that lasted for something like 6 weeks. For 6 weeks, we cannot talk to the spacecraft at all. But still, probe is perfectly fine, doing everything we wanted to do on its own. And as I said, we waited for 60 years, but this is the moment. It was back in 2018, August 2018.
10, 9,
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
3R68 look good in a full thrust mode. "25 seconds into flight. Chamber pressures continue to look good on all 3 boosters."
So, okay, this was in August 2018, and
pressure on the core booster is throttling down to the partial thrust mode.
So this was back in 2018 when we launched Parker Solar Probe. And it was really intense moment there because I've been working on this mission for something like 10 years until the launch. And the team is, there are hundreds of people who worked on this project. And you know what? You have this spacecraft that it's so dear to us. We invested so much into it. And you put it on top of the most powerful rocket ever built, a Delta IV Heavy. And anything you wish for is just please keep it safe and bring it up there in space, because we don't want anything to happen to it. And let me tell you a little story about it, because when we were launching Parker Solar Probe, there was actually a clock on the wall that starts from the launch and counting from the launch pad. And I was so focused on the rocket going up, what seems to me like 30 seconds, I turned back and it was actually more than 5 minutes. You don't really realize because you are so focused. And obviously, I think many of us were really stressed because if something goes bad with this, it's really a huge setback for so many people that were involved in this team. But obviously, it was a huge success. And this is part of the team. This is just our folks here at EPM. This is an operation team. So what you see really joy on the faces of everybody. Some of them are a little bit emotional as well, because we invested so much into this and we wanted it to be a huge, huge success for all of us. And by the way, when you say huge success for all of us, by all of us, I mean mostly the young folks, the young people, because they are the most who are going to build their careers on a mission like this one. So that's what we want. And a mission like this one is for you as well. The data we are getting from this one will serve scientists for decades to come. And if you are interested to work on it, I'm pretty sure there is so many discoveries you can do with the data that we are getting from Parker Solar Probe. Anyway, this is the probe. This is the spacecraft. And as you can see, it's not really a big spacecraft. From the top to the bottom here, it's about 3 meters, a little bit more than 3 yards. That's what it is. But the ingenious invention that enabled us to realize the mission is this piece of technology here, the heat shield. Without the heat shield, we don't have a mission. That's actually what stands between the sun and the probe itself. So on Christmas Eve this year, December 24, 2024, the side of the heat shield that is facing the sun, this white side here, will endure something like 1400 degrees Celsius. That is enough. That is 2500 degrees Fahrenheit. That is enough to melt steel. About 1 yard behind, it is room temperature. And that's the magic of it, because the heat shield is so efficient in dissipating heat that basically 1 yard behind we are at room temperature, and that's where the body of the spacecraft works, and also most of the instruments are working there because they work all at almost room temperature. And this is just an animation of how probe makes it from the Earth, fly by Venus. By the way, Venus is really our closest friend because it helps us get closer and closer to the sun every time we fly by it, and that's our sun. And Parker Solar Probe flying through it. So when you see the eclipse on Monday, if you are going to see it, and hope you will see it, you think that Parker Solar Probe is flying through the sector that you will see during the total solar eclipse. And that's actually what is happening. So, okay, Parker Solar Probe is designed to do so many things. And some of the things it designs to is to study these big explosions on the sun, like the coronal mass ejections. Some of them I showed you earlier. And we want the sun to do its best, really, give us the strongest events ever, because that's what we want to study with Parker Solar Probe. And we got our wishes. On September 5th, 2022, the sun launched one of the most powerful events ever recorded. And Parker Solar Probe happened to be very, very close to the sun. And this is the other thing about it as well. Parker Solar Probe was on the other side of the sun. And for days, we didn't really know whether Parker Solar Probe was fine or not. We needed it to get on the other side of the sun to learn, yeah, everything was fine. But listen to this. So if you were on board the Parker Solar Probe, you will get probably a view and the view and also probably the sound we are hearing here. The sound we are hearing is basically that coronal mass ejections coming toward Parker Solar Probe, and when the shock wave hits Parker Solar Probe, you get this snap in the audio that you can hear clearly. Let me play it another time that you can appreciate it. And by the way, this event was flying at more than 2,500 kilometers per second. So yeah. By the way, let me back it a little bit because I really love this movie. And, what you will see in a little bit here, you will see the Milky Way crossing the field of view of the instrument. So that's the CME that is passing by. And this is the Milky Way. It's there. So okay, let me go a little bit into the future now and tell you that Parker Solar Probe, what it did for us, it is giving so much data that we needed for so long to understand the sun, and we cannot really complain at all. We are getting way more than we need with Parker Solar Probe, but there is also Solar Orbiter, there is DKIST. There are plenty of assets out there. But what missions like Parker Solar Probe do to us, they open our eyes and basically lead us to be bolder and bolder than ever before. Now what we think for the future, and when I say the future, is basically, it's people like you. You are the future. We are merely the present now. So we are thinking about other programs that are way more audacious than Probe, than Orbiter, and one of those is those mission concepts we are thinking of now is, instead of observing the sun with one spacecraft and just from one side, we want to look at it from all sides, like really a 3D thing. That way we don't lose anything. We will see it from all angles. And that will help us solve some other mysteries that have to do with the solar interior, some other to do with the atmosphere, and also much further out, like space weather, the effects of space weather. And this mission is basically a constellation of spacecrafts that we will launch here from Earth. We will have multiple launches from them. Some of them will stay in the plane of the orbit of the Earth that we call the ecliptic, but some of them will go all the way out to Jupiter to get a gravity assist and go out of the ecliptic to observe the poles of the sun. So with this constellation, when it comes, and by the way, this constellation in terms of size and cost and everything is way bigger than Parker Solar Probe, and for it we really need people like you. We need people like you to help us build this mission, but also do the science with it and build their career on it. I'm leading this mission, but if I do it because I want really young folks to come in into this community and help us understand some of these big mysteries about the sun. As I said before, the sun is our star. Without it, we cannot live, but it also can harm us in some ways. So the best way to do it is to understand how the sun works. And it's with missions like this one that we will do it. But there are so many other ideas out there. So in a way, what I want to convey to you, opportunities are plenty out there, and they are just waiting for people to jump on them. And anyone out there can do it. Let me go back to myself. I was born in a country. Well, what I studied there is really physics. I was good at it. I will not hide it. But I never studied astrophysics or space physics or anything like that. but still, I worked hard for it, and I'm so grateful that I got guidance from my parents first, but also from my teachers, from other folks who guided me along the way and helped me to get where I am now. And I'm so grateful for all of them. So anybody who dreams of something can do it. And this is really the message I want to close with. The other thing I want to say, I was talking about this mission here at a meeting in Europe last year. And somebody came to me saying, now we are going to realize Star Wars. And I told him, why not? If it's going to help us, why not? So I wanted to close with this because I opened with Star Wars back in Tunisia. Firefly is like Star Wars as well. So with this, I want to stop here, but I'll be happy to answer any questions you may have. So please go for it. Thank you so much. This is really makes not only my day, it makes the week, my month, my year. I really appreciate that. That's really nice. And when I'm visiting Hawaii next time, I'll be happy to come and visit you in person. That would be really definitely a pleasure for me. So
Wow.